Okay, what have we learned so far about potential energy diagrams? They are visual representations of the change in the amount of potential energy throughout the chemical process. And over here is the potential energy diagram for exothermic reaction, the reaction that produces energy alongside with the products of the reaction. So over here, there is the initial potential energy of the reactants. Right here, there is a potential energy of the products. This is the amount of energy, potential energy of the products. The difference between those two levels would be heat of reaction. Heat of the reaction is the difference between potential energy of the products minus potential energy of the reactants. So over here it's 110 minus 1000 equals negative 890 kilojoules. And this little bump over here, this length, is the activated energy. So let's call it letter C. The activation energy. The energy that is needed uh, to initiate the formation of the activated complex, the short existing complex between the methane and oxygen with the heightened amount of potential energy from which it will be able to proceed and complete the reaction forming carbon dioxide and water. The energy of the activated complex itself will be this long arrow over here. So the D is potential energy of the activated complex. Okay, this reaction is exothermic. We know that because we see that the amount of reactants, the amount of potential energy in the reactants is significantly higher than the amount of potential energy in the products, and through that we have a negative heat of reaction value. It's 890 kilojoules of energy that has been released with the production of carbon dioxide and water. Now, let's look at the reaction that is endothermic, the one that is actually absorbs energy at it. So, oh, my picture's not here. Ah, there, here it is. Let's move it aside, let's move it in. Okay. Over here, my reaction, if I write it down, looks like this. Nitrogen reacts with oxygen to produce 2 moles of nitrogen monoxide. And this reaction is exothermic. I can tell it even from the shape of this potential energy diagram. My reactants have low amount of energy. My product has higher amount of energy. So if I will calculate the heat of reaction for this one over here, it will be potential energy of the products minus potential energy of the reactants. So we're talking about 1200 kilojoules minus 1020 kilojoules 180 kilojoules. The number is positive. This is a clearly endothermic reaction, the reaction that apart from having nitrogen and oxygen also absorbs some heat for it. So to once again identify what is what, here is my A. A will represent potential energy of reactants. Right here, this letter B, will represent potential energy of products. The difference between them, this blue arrow over here, will represent heat of reaction. And as before, my reactants first need to achieve some excited state, some higher energy state to form the activated complex. So here is the place of the activated complex. Okay. And to reach it, this is the amount of energy that my reactants need to absorb. So my activation energy line, this is my activation energy. That will be my C line. C line represents activation energy. Activation energy for endothermic reaction is so high that it is unlikely for this reaction even to occur because it takes huge amount of energy to even become an activated complex. And this letter over here, the letter D, from here to here, D will represent the potential energy of the activated complex itself. You can clearly see that the shape of the diagram, potential energy diagram, suggests whether you are talking about exothermic or endothermic reaction. Our exothermic reaction will look something like that, while our exothermic reaction will have a low starting point and higher ending point. So this one over here is exothermic reaction potential energy diagram, and this one is endothermic reaction.